penultimate talk in our series this year. I think we've got one more, haven't we? This year, we've got two. So my name is Dr. Leonard Kidger. I work at HPE. I also was an academic in my past, but moved on to the dark side of industry. And today, because of my contacts with work, I've got Tim who's going to do the talk. He's going to do an introduction himself, just to say that he joined Cray about 17 years ago. So he's been with the company a long time. As one of you will know, big companies absorb small companies. So Cray became part of HPE about 5 years ago. But that's all I want to say. Over to you, Tim.
Thank you. I'll just correct that to 7 years ago rather than 17.
Oh, 17.
But yes, I'd have been it's a little young to start at Cray back then. But, anyway. So hi, everyone. Yep, my name's Tim Dykes. I'm a senior research engineer at Hewlett-Packard Enterprise in a group called the HPC and AI EMEA Research Lab. And I'm going to talk today about Cray Supercomputers, a bit of a past, present, and future. So in general overview of the talk, I'll explain a bit more about who I am, why I'm here talking. I'll explain what exactly a supercomputer is or how we define it. Then a bit of discussion about the past, where it all began, how we got from there to now, to the modern day supercomputers that we build and sell at HPE. The present, I'll talk about what a modern supercomputer looks like. And the future, some ideas of what a future supercomputer might look like, and a bit of discussion on the kind of research challenges we face with modern supercomputers and everything that's coming up. So, who am I? And I've got some notes just on paper if you see me rustling, just so I remember what I'm saying. Yes, I have a PhD in a mixture of high-performance computing, astronomy, and computer graphics or visualization, based at the University of Portsmouth in the UK. And during my PhD, I did an internship with Cray in Bristol. That was in 2016, working on distributed visualization for large-scale astronomy data. And once I finished my PhD, I was hired to work at Cray, and that's in Bristol back in 2017, where I've worked since. Cray was, of course, acquired by Hewlett-Packard Enterprise late 2019, and so we're now part of the big HPE family. But I'm still in the group that I was in when I first joined Cray. So yes, my current role is senior research engineer. The lab name is the HPC and AI EMEA Research Lab. And I work on quite a few different things, including internal research and development projects, what we call advanced collaboration centers, which are collaborative groups with some of the larger systems that we sell, alongside supporting on customer procurements and various other things. This is a picture here of me, slightly younger and fresher faced, standing in front of one of the supercomputers we've sold. This is to KTH in Sweden, a couple of years ago. If you do have any questions, by the way, while we're going, just feel free to shout out, stick your hand up. Otherwise, there'll also be time at the end of the talk for discussion. So the group that I'm in, this is just a sales slide for our group to explain who we are and what we do. We focus on deep technical collaboration with the industry, academia, and public sector, both customers and non-customers. So we're interested in working on technical problems related to high-performance computing and AI. And we, in general, focus on these long-term relationships surrounding research, co-design, sometimes operational support when there's problems with the system that are deeper than just a broken stick of RAM that you need to replace or something, that really need us to look at the technology that we're using on the system and maybe think about designing new technology, new products, et cetera, et cetera. We have lots of different research interests in our group. Our group is about 15 people or so, and we cover quite a lot of different topics. We engage in various different ways, so I won't go into too much detail on that. I'll jump sort of into the meat of the talk. So as a starting point, I want to explain what we consider a supercomputer. And the definition I use, at least, is that it's the most powerful class of computer available at any given time. And now a supercomputer 50 years ago was a very different looking machine to a supercomputer now, but we still called it a supercomputer. And so the technology has changed a lot. but our basic understanding of how powerful a computer is hasn't actually changed that much. And so how we make a computer powerful, how we make it super, and what that really means, I'll talk about in the next slide or two. But just from a terminology perspective, I want to quickly cover supercomputer versus cluster or cloud. These terms are thrown around a lot, and just so we're all on the same page here, the way I define a supercomputer is that it's the full system architecture has been designed from the ground up for bare metal performance and efficiency. Whereas if you think of a cluster, this is more of a catch-all term for any multi-node parallel system, generally off-the-shelf construction, pieces put together to form a parallel system. And then you have cloud and hyperscaler systems where the design priorities favor things like flexibility, elasticity, virtualization in particular, multi-tenancy, etc. Now, the differences between particularly cloud and supercomputer systems are shrinking, but this is how I'm defining those terms, at least in this talk. So what exactly is a recipe for a supercomputer? How do we make a computer powerful? So firstly, we select the best microprocessor. So a good CPU or processor of some kind is the core of your machine. Then we surround it with a bandwidth-rich environment, local memory and interconnection network, ways to get a lot of data to the CPU and between CPUs. We then scale that system up. And so we use a very large number of processors. We do things like try to eliminate any interference the operating system or any other system software might introduce. We design in reliability, resiliency. There's many components in our systems that might break. So we need to be sort of designed in reliability there, provide scalable system management, I/O, programming and performance tools to enable you to use the system and sort of support it over its service life. So this is our recipe for a supercomputer. And I'm going to talk a fair bit more about how we build these. But firstly, I want to discuss how super is your supercomputer. So I said on a previous slide, this is the most powerful class of computer available at any given time. But how do we measure powerful? So in general, this is workload dependent, right? It does depend what type of problem you're trying to solve. But the traditional view, and in many cases, this is number crunching. So how many numbers can you crunch and how quickly can you do it? So relevant metrics here are essentially floating point operations per second. So this is things like multiplications, additions, subtractions on real numbers. This is how many operations can you do on those numbers per second. And we'll frame a lot of the history section of this talk in flops. And this will go from sort of 1 flop per second up to 1,000 flops or kiloflop, megaflop, gigaflop, up to an exaflop, which is 10 to the 18 floating point operations per second, which is really a lot. And so how do we gather these metrics? Well, essentially, we have a de facto benchmark called the LINPACK benchmark, or HPL, that if you're interested in how super your supercomputer is, you're likely to run this benchmark and collect together some numbers and submit them to the top 500 list. The top 500 list is a global list of the top 500 supercomputers in the world. This list is updated every 6 months, and it's used as, in general, the metric for who has the biggest and the best supercomputer. So I show the top 10 on the right-hand side of this, which I thought wouldn't be readable, but actually it doesn't look too bad. So this is the current top 10 from the last published list. And we see number 1 here, Frontier. I'll talk a bit more about that later because that is one of our systems. We also have the number 2, Aurora, an Intel-based system. Number 5, Lumi, which is an AMD-based system and the largest supercomputer in Europe. And then you see various other systems from other providers such as Eviden, NVIDIA, IBM around there, and Fugaku from Fujitsu out in Japan. Microsoft up at number 3 there. So in general, this is how we determine how super your supercomputer is. And if you have a super supercomputer, you'd submit your numbers to this list and see how high you get. So we've covered what exactly we consider a supercomputer and how you define the term super. What I'd like to sort of go into now is the past section of my past, present, and future slide deck. And we're starting with a very brief history of HPC. And part one is digital computing, because high performance computing in general is of course tied to digital computing. Now, this is a brief history. So for those history buffs amongst you, if you don't see your favorite machine on this list, it's not because I don't like it or that I think it's rubbish. I'm just trying to cover quite a long history and quite a small side. So I've only picked a few key machines through here. So, I mean, before, say, 1920s, 1930s, computing was really a manual exercise. Computers were humans, and they were mostly female. And they sat and they worked out tables, doing arithmetic in their heads. And this was how you did large-scale mathematics, essentially. Now, in the late 19th century, we started to have electromechanical machines. So these are mostly mechanical tabulators using things like cylinders, wheels and discs, punch cards, bells, whistles, all sorts to do electromechanical computing. And it was only in sort of the 30s and 40s that we started to see some progress beyond this. And so as you'll likely be aware, in the late 30s, we had a fairly strong military requirement for compute. People started caring a lot more about quickly computing things like trajectories and cryptography and these types of problems. But we were still we were at like one floating point operation per second, if that. So these machines were still very, very simple. As we got into sort of the late 30s, the early 40s, we started having some large-scale efforts to build digital computers. We had the Mark I, which started construction in 1939. This was eventually used in the Manhattan Project. This was still an electromechanical machine. 1939 was incidentally the year that Hewlett-Packard was formed in Palo Alto in a garage, and this, of course, eventually became part of HPE. So then as we progress into the 40s, we have a lot of British efforts on cryptanalysis machines like the Colossi systems. Designers started moving to vacuum tubes to increase switching speed. You have things that machines like ENIAC, which, and up here you're getting to from 0.4 kiloflops per second, so 400 floating point operations. So we're making slow progress, but it was progress. Throughout the 50s, we had continued improvements. Transistors slowly started making their way into computers with things like the Bell Labs machine, 1948. They became smaller, more reliable, generated less heat. They could switch a lot faster. And by the 60s, we started having some nice transistor-based systems like UNIVAC LARC, Atlas, and we started getting into the megaflop range. So if I jump over into the next slide, meanwhile, while all this was going on in a small town called Chippewa Falls out in the US, a young boy called Seymour Cray was using Meccano to make a machine that would read in paper tape and output Morse code. This was back in 1935. A little bit later on, he joined ERA as an engineer working on some very early computing machines. And so that's Engineering Research Associates. They were bought by Remington Rand a little later on. The ERA 1101 was rebranded the UNIVAC, which is a name that some may remember. And sort of around 1953, Seymour Cray was one of the first machines he was credited with working on was the UNIVAC 1103. And so some of the interesting features of this is that it had this one of the early machines to use magnetic core memory, which is a type of non-volatile memory based on rings of magnetic cores, which was used almost universally up until we came up with sort of semiconductor-based memory. And for those of you who may have seen a core dump when you're writing some code and it crashes, that's where the term core in core dump came from, actually, because it used to be core memory. Anyway, so Cray joined CDC, or Control Data Corporation, which was a company founded by ex-ERA employees that weren't really happy with the direction things were going at Remington Rand. And that was in the late 50s, and they started working on transistor-based designs for large supercomputing systems. So one of the first supercomputers that we consider is the CDC 6600. So this was a Seymour Cray-led design. He's the lead designer on this. And this was built of a single processor. So we have a picture that this is the machine in the top left of this slide. A single processor clocked at 10 megahertz, and you get somewhere between 1 and 3 megaflops of performance. That cost $8 million at the time. So it's about $60 million in today's money. So even back then, they were expensive machines. These were made up of logic blocks, like the one in the top right of this image. Nearly 6,000 of those made up the CPU, and they were hand wired. They had 64 transistors on, visible with the naked eye, and so it's a very different time to today. So you can see a mobile chip in the picture below that, which has billions of transistors, of course not visible by the naked eye. So we've really come a long way, of course, since then. In 1972, Cray started his own company under his own name, Cray, and released the first Cray supercomputer in 1976. We have a picture of it in the bottom left here. It was called the Cray 1. And so it was the 50th anniversary of Cray research not too long ago, 2022, and there was a bit of a celebration at the company. And if you visit the National Science Museum in London, you'll see one of these machines on display, so you can go and have a look at it. And so even 50 plus years later, Cray's name lives on. While he does not, we still sell machines branded under the name Cray. And Hewlett-Packard Enterprise, the company that we work for, builds and sells supercomputers, components, accompanying software, as well as various other things. So then moving into the second part of the brief history of HPC, what I'm calling here the Cray era. And this is a history very much focused on Cray. There were other machines, other companies, IBM, etc., building machines, but this is a Cray-focused discussion. So off the back of the CDC 6600, can you see if I wave a mouse around it? You see? Okay, so I'll use the mouse just to highlight a few pieces. So we're coming off the back of the CDC 6600 in the mid-60s, and we come into the 70s at sort of around 1-ish megaflops of performance for the best machines, and we released the Cray 1 in 1976. This was actually the same year that the Apple 1 got released, so which obviously then turned into the Macs that we use today. So we have essentially the microprocessor revolution of the 70s and 80s here, where we started building better and better integrated circuits. And we had a sort of period of incremental improvement marked by a bunch of different machines that we've built. So we had the Cray XMP, which was 2 processors. So just to reverse a bit, the Cray 1 was essentially, let's just quickly run back to this slide. So we'll go on to the Cray XMP, which included 2 shared memory vector processors. As we progressed through the 80s, we had the Cray 2, Cray YMP, which had between sort of 1 and 8 processors, and this was where we reached about 1 gigaflop of performance. And as through sort of the 80s and early 90s, the commodity general purpose CPU became sort of better and better. We were, up until then, we were still building our own processors at a fab in Chippewa Falls. But yes, in sort of the early 90s, the general purpose CPU overtook custom-built processors in cost effectiveness. And we sort of had the first massively parallel processors with machines like the Cray T3D, which included DEC processors. So that's Digital Equipment Corporation, Alpha RISC processors between 32 and 2048 over the various versions of T3D that were released. And then we continued through this period of incremental improvement, bigger processors, more of them, better performance, building bigger systems. We have the Cray T3E, which sustained 1 teraflop of performance. So, you know, each of these is 1 order magnitude more than the last generation here. And this trend of incremental improvement continued right up through the early 2000s. So we have the XT5 around here somewhere, 2009-ish, which was the #1 supercomputer at the time. First Cray branded petascale machine with about 200 cabinets, 200,000-ish AMD Opteron cores. Although the first machine that achieved the petaflop was actually the IBM Roadrunner. And so various different machines throughout the early 2000s up until what our current machine line is called the HPE Cray EX. This was the first machine to reach exascale, or 10 to the 18 flops per second. And so let's see if that's skip to the next slide. So over the years, you can see we had a variety of different supercomputing designs. Cray 1, which had this sort of iconic C-shaped design. Cray 2, which was actually entirely submerged in liquid coolant, and various different designs going through up until sort of the early 2000s, when they started to homogenize in terms of looks, lots and lots of cabinets, and they said that that's what they look like today. And we sold these machines to various different types of customer, government customers for things like weather forecasting, intelligence agencies, national HPC services. We still do these types of sales, manufacturing, commercial customers, oil and gas, automotive, et cetera, academia. So our customer base has remained fairly constant over the years. So where we've ended up is the HPE Cray EX. This is the largest system that we sell, and currently the largest system in the world, the Frontier EX system at Oak Ridge National Labs in Tennessee. That's 1.1 exaflops of performance as measured on HPL. At the time, it was also the most power efficient at 52 gigaflops per watt. And this is built of 74 EX cabinets. So each of these, you can see sort of 3 cabinets lined up before a CDU for cooling, and then another CDU, 3 more cabinets, et cetera, et cetera. So 74 cabinets, about 9,500 AMD CPUs, almost 40,000 GPUs, almost 40,000 network interconnects, a lot of storage, 700 petabytes, a lot of cabling. So 90 miles of cabling for the Slingshot network, which is our own interconnect that we design at HPE. It's a very big system. It weighs almost 300 tons in total, and it's comprised of roughly 60 million individual components. So they're big, they're complicated. But what exactly is a modern day supercomputer like this made of? So you can see a lot of hardware, cables and tubes and things. What exactly do we put in these machines? So our basic system building block is a node, or a compute node. And so the Cray EX is a massively parallel processor. We put thousands of nodes together to form a distributed system. There are two basic types of node. One is the compute node. These are only used to do user computation. That's what the bulk of the system is made up of. There's also non-compute nodes, and there's various types of these, and they perform other tasks for the system to function, things like storage, user access nodes, the nodes that you log into when you access the computer, visualization nodes, various other bits and pieces. Now, the hardware for between 2 and 4 nodes typically is grouped together into a compute blades. And this is the diagram we see in the top right here of a compute blade with 2 nodes on. And I'll show you some more pictures of blades and things as we go through, but you can see inlets and exit for liquid cooling coming in there, and power and management connectors at the back here, and then a bunch of hardware in the middle. So here's some real-life pictures of compute blades. These are the CPU blades that we have in the Archer system. So this is the UK National Supercomputing Service. These are AMD CPU blades. So each blade, each node has 2 AMD CPUs, and we have 4 nodes per blade. And so if I get my mouse out again, then the nodes are organized in rows here. So you've got a NIC, this card here. Underneath it is another CPU, and then a CPU here underneath these copper cooling pads. You've got the memory on either side, and then we move on to the next node. 2 more CPUs, NIC, memory, etc. Some board management, controllers, and power routing stuff. In the middle, 2 more nodes. And everything in these devices are liquid cooled. So you can see these little jackets on the memory. We liquid cool memory, the CPUs, the NICs, everything. We build different types of blades depending on what hardware you want. So this is a GPU blade, AMD GPU blade. So we only fit 2 nodes per blade here. And you can see it organized sort of in the left half and the right half. Each half has 1 node. 1 node is made up of an AMD CPU, which is under this NIC here, some memory, and then 4 GPUs, which are again liquid cooled at the top here. And the second node of the same design on the right-hand side. One more, just for example's sake. This is an NVIDIA GPU blade. And so this is the Grace Hopper Superchip, a recent blade that's going in the Isambard AI system that's being installed in Bristol fairly soon. And again, you can see we have 2 nodes. They're organized a left half and a right half, but shaped slightly differently. So these nodes are all connected together via Slingshot. This is our interconnect. We've had so we build our own interconnects at Cray and now at HPE, and we have done for many years. We had C-Star, I believe, was one of the first, Gemini, Aries, and now Slingshot, various generations of interconnect or network that we use to connect all of these together. Our most recent one, Slingshot, is an industry-leading high-performance interconnect. It scales very, very high. It has some interesting features about hardware congestion management and adaptive routing to let different workloads run together in a nice way. And particularly interestingly, it's Ethernet compatible, which many of our previous networks weren't. So we connect all of our nodes, both the compute and non-compute nodes, together via our Slingshot interconnect. And then you put your blades, your interconnect, and all the other pieces you need for power and cooling, etc., together, and you get a machine that looks a bit like this. So you recognize this from the Frontier picture. We have compute blades organized into chassis. So you can see those compute blades we saw earlier, 8 of those lined up, use the mouse rather than my arm, 8 of those lined up vertically here, and then 4 rows of chassis. So 8, 16, 32 blades, and then another 4 on the other side. So there's 8 groups of 8. In the middle, you have rectifiers. On the right-hand side, power distribution units to allow you to get power from sort of coming into the machine to all the different pieces of hardware. Cooling manifolds at the front for all the liquid cooling that goes to route water in and out of these blades. Switches are actually mounted horizontally on the back, so you have vertical compute blades, horizontal switch blades, and then so they're mounted in the back half of the cabinet. These are in the front half of the cabinet, and then they're connected all together. To get your cabling everywhere, there's cooling manifolds back here. Our switches are liquid cooled. Oops. And so there's not actually a single fan in a standard EX cabinet. Everything that we need to cool is done by liquid. So this scales up from 1 to hundreds of cabinets, up to 64 blades per cabinet, get up to 512 CPUs or 256 GPUs per cabinet, hundreds of thousands of nodes. We have 3 exascale systems in construction, one of them being Frontier that's already at exascale. Aurora's number 2. It's only halfway there because we haven't finished building the system yet, but it should be 2 exaflops when it's completed. And then we have El Capitan as well in the US, another AMD-based system. And then there's lots of petascale systems in construction and delivery as well. So this is essentially the EX system and what a modern supercomputer looks like. What about the software environment? So what kind of software do we put on these machines? So this is a picture of our software stack. I'll start at the bottom. Hardware, obviously the system, so HPE Cray EX supercomputer. On top of that, we've got the firmware, low-level system management stuff, turning things on and off, deploying BIOSes, all that kind of stuff is done with the Redfish API. Above that, you have your system management software. So this is a high-level interface for managing a large-scale distributed system, things like deploying OS images, software packages, user groups, node management, security, authentication, all these kinds of things that you need to do to get a very large distributed system operational. And that's either via, we have 2 solutions actually, one is CSM and one is HPE CM. And then we have the operating system. This could be HPE Cray, so these quite configurable systems. So there's different types of OS and software that you can put on them. But you have either HPE Cray OS. So we used to, we still have our own OS, but it's based on SUSE. We used to have the Cray operating system, which was entirely owned by us back when we built the processors too, and that was the operating system you'd have on like the Cray 1, the Cray 2, et cetera, et cetera. But for a long time now, we've based our OS on essentially a cut-down version of a standard Linux distribution with a few extra bits and a few bits cut out. You also have SLES running on the non-compute nodes, and there may be support for other Linux distributions, Red Hat, etc. One level up, you then have your workload management software. So someone needs to organize, we may have thousands of users on this machine. It has hundreds of thousands of cores to be organized. People need to share this. We need to have some reasonable way of managing the workload, managing the jobs that users want to run. And then sort of ensure that this machine can be shared reasonably amongst all the people trying to use it. So the Slurm or PBS workload management tools are sort of the de facto ones we use for managing workloads on these systems and scheduling jobs, et cetera, ensuring everyone gets their fair share of the machine. Above that, we have the tool chains. So our Cray programming environment, we have our own compilers, particularly for Fortran and C, C++, but we also support vendor-specific tool chains, and these are the things you use to compile your code so that it runs as efficiently as possible on whichever vendor hardware you have in your machine. So we're a system integrator. We provide the system, which has an optional type of hardware inside, right? I showed you NVIDIA nodes. I showed you AMD nodes. There are also Intel nodes. And so it's quite a configurable system, and we allow you to run the different vendor tool chains you might need to use to get your code running efficiently on the hardware that you've chosen in that system. And then, of course, above this is applications, and they're the things the users bring. These might be C or C++ applications, they might be Fortran, they might be Python. More recently, they might be things like TensorFlow and PyTorch AI applications that have middlewares that need to be supported to run optimally in a distributed way on these kind of systems. So that's a brief overview of the software stack on our system, and in general, a brief overview of the modern supercomputer that we sell. So next, I'd like to quickly make a few comments on what the next supercomputer might look like. So if we think about how we got to this point, in general, the performance gains we see in supercomputing systems and general computing systems are based on either hardware innovation or system size. Right? Either your hardware gets better or your system gets bigger. It's fairly simple. And hardware innovation is coming through either incremental improvement of existing architectures. You know, we add more cores to our chip, we deepen the pipelines in our chip, we essentially make our chips better, or increased architectural specialization. So we modify the architecture to better support specific workloads. And this might be things like GPUs, other types of accelerator, or you might have things like post-CMOS technology, so radically new types of hardware. These are the three routes that we see to hardware innovation. And so I'm saying here that, however, this is difficult, right? So hardware innovation in general is difficult. Physical limitations mean that incremental improvements have become increasingly slow, expensive, and complex. Architectural specialization can be difficult because it's difficult to replace an entire system with one technology. You typically need the right technology for the right problem. And then post-CMOS technologies, well, the path from lab demonstrator to new chip technology in a commercial fab is very long, historically 10 plus years. So if we're talking about something we want in a supercomputer today or in a supercomputer tomorrow, it's not going to be a radically new processor design. So in terms of building bigger systems, there are also limitations on just how much power and just how much money you can spend on any one system. So Frontier was something in the region of $600 million-ish, a system of that size anyway. Electrically, it uses about 30 megawatts of power, and that's to get you sort of 1.5 exaflops. Now, if you're trying to move another order of magnitude beyond that to 10 exaflops, say, you're not really going to want to spend 10 times the amount of money or supply 10 times the amount of power. 300 megawatts is a big ask. So in general, it's difficult to imagine that the system just keeps getting bigger. And it's also quite difficult to imagine that hardware innovation continues at the pace it had, at least particularly through sort of the 80s and 90s. So one option might be more heterogeneous or modular system architectures. So architecture specialization is one of the more practical paths to performance growth. We put a variety of accelerators in a variety of places for different kinds of workloads. So if you think at the top, you have your applications or workflows. Underneath that, you've got system software, middleware. Underneath that, the compilers and programming models that allow you to run on specific hardware. And underneath that, you've got your system that could be a modular system architecture that has different types of hardware in different partitions to allow you to run different kinds of workloads. This might be sort of data ingestion coming in from your IoT or edge into your high-speed network that may have a built-in accelerator to do collective operations in hardware. Then you might have a dense CPU partition for things like simulation and analytics. CPU plus accelerator for simulation, maybe dense accelerator for your machine learning AI workloads, maybe reconfigurable accelerators for high throughput workloads, data reduction, this type of thing, and maybe storage with built-in accelerators for post-processing. So moving the processors to the data for different types of computation. It's one route forward. In terms of general challenges for the future of supercomputing, I've just listed some of the research topics that we feel are important and things that we focus on in our day-to-day work in the research lab. This is particularly AI systems and software, so I think everyone's aware that AI has taken the world by storm, and there's a lot of work going into making large distributed systems that can support the training and the different kinds of workload that AI users need, and these do need large systems. We've seen this sort of convergence of big data or high-performance data analytics, AI, and HPC. These workloads are mixed, and we need to be able to support that and understand how we get workflows that do very different types of work working together. And that leads us into things like hybrid cloud and federation, where we have cloud systems and HPC systems working together and with different sites federated such that users can use different machines with different types of hardware under the same type of access, same type of identity management, etc. Workflow computing, so connecting together different applications, moving data between them, allowing different applications that run on different types of hardware to work together. The diverse architectures that we're seeing in supercomputers. I showed you just a few examples of different types of hardware that we support. There are others. And so being able to support those and allow people to build their code and run them optimally in a large distributed system with diverse architectures can be difficult. Heterogeneous systems, so not only are the architectures diverse, but we're trying to use a lot of different types of architecture in the same system, and that makes it heterogeneous. And writing efficient software that can run across a wide variety of architectures in the same system can be quite difficult. Research problem to focus on there. Performance portability, so getting good performance on all those different architectures is a problem in itself. Energy efficiency is grown in importance lately, both in our own homes, but also at data centers. Monitoring and operational data analytics, so this is understanding what's happening on our system, how do we improve and optimize system operation by monitoring the behavior of the hardware, the applications, and all of the software on these systems. So these are just some of the topics that we see as being important and challenging in the future of supercomputing. And I just wanted to say a couple of words about a couple of these topics. So firstly, AI systems. As-empowered AI is one of the more recent systems that we've sold. This is being installed in Bristol. It's part of a large government investment to transform the AI computing capacity of the UK. And they've invested in 2 AI research facilities, or AIRs, one of which is Isambard AI based in Bristol. This will have over 5,000 next generation NVIDIA GPUs. They'll be put in 12 Cray EX 4000 cabinets, connected together by our interconnect. It'll look very much like the image you saw earlier. This is being placed in what we call a modular data center in Bristol. And this is a data center essentially made out of shipping containers, very quick to put together, very easy to place somewhere. It means you don't have to build a very large and expensive data center to host some very, very big equipment. This project is being led by University of Bristol's Professor Simon McIntosh-Smith and Dr. Sadaf Alam, and we have a picture from his Twitter here of the first phase of the machine has just come live. And you'll see later in the year the rest of the machine pop up, and it will become available for people to use, funded by the government as an open AI research facility for people who are doing AI research to apply for time on and use this system. Energy efficiency, as I mentioned, is a very important topic for us. When the recent increase in energy prices affected all of us, it also affected the data centers, and you found a lot of folks who had a 5-year forecast of energy costing for their supercomputers suddenly discovered their budget wasn't big enough because energy went up for everyone. And many of them came to us and said, can you please help us use less energy so that we can keep the lights on in our data center with the budget that we currently have. And so this affects everything from the data center up to the application. That's why I have this stack diagram. There's opportunities for optimization for energy efficiency all the way through this stack, from green data centers and carbon neutrality to really application level prioritization of energy to solution rather than time to solution. We almost always care about how long it takes us to complete a particular job, to have one of our applications run and get a solution. But we don't usually care about how much energy that takes. And so prioritizing energy to solution is one topic of interest.
Does the energy usage include the cooling?
Yes, it does. And so the full, the 30 megawatts number here does include cooling.
Just wondering about energy efficiency. How would that be done? Would that be in market levels, something to do with how implementations have been done? Or a different approach with the architecture? Or how would that be?
Yeah, so there's sort of many opportunities throughout this whole stack to try to improve your energy efficiency. So it could be at the data center level, finding more efficient ways of cooling your system. So some recall exactly how long ago it was we moved to using warmer water for cooling because we found that it was essentially more energy efficient to use warmer water and let it heat up a little bit than use cold water and let it heat up a lot. We have, so the Lumi supercomputer, which is the largest in Europe at the moment, is actually placed off in the middle of Finland, a very remote location and powered entirely by hydroelectric power. And they've done lots of work at the data center level to try to improve the energy usage. But it goes all the way through the stack. So when it comes to the specific system, it might be the type of hardware you choose to put in there. It might be the way you configure that hardware. So at the node level, you might choose, and actually the folks at Archer, the National Supercomputing System, did this. They chose to downclock the CPUs. So the default clock rate for the CPU, I believe, was somewhere around 2.5 gigahertz, and they downclocked it to 2 by default because they found that this didn't significantly affect the performance of the general applications that they have, but it did save them a fair amount of energy. And so the users can override that if they want, but the default setting is actually now downclocked for all the CPUs on the system. And so there's various other areas where you can look at sort of how to prioritize your energy usage. In fact, I've just got 1 or 2 slides on some work related to this. So we had an intern, Alex, working with us from UCL, and he worked on building a scheduling simulation for Archer 2. And so the scheduler, as I mentioned before, the workload manager, is responsible for scheduling jobs on your system and deciding which jobs should run, when they should run, and where they should run in the system. And what our intern did was build a small scheduler simulator so that he could replicate the scheduling behavior of the Archer 2 system and run this on historical data and get a reasonably accurate simulation across different quality of service classes. And then he could use that simulation. Oh. Well, that's unfortunate. There should be plots in this square. But I've had to move the slide deck onto this computer, and it seems to have come without the most interesting plot of the slide, which is inside here. What he did essentially was adjust the order in which jobs were scheduled so that the high energy usage, or the periods where very large jobs were running, were outside of peak energy usage times. And so he found that by adjusting the simulator schedule, he could actually reduce energy usage just by pushing jobs into different times of day without significantly impacting the amount of time people have to wait for their jobs. And I'll share the reference to the paper afterwards so you can see full details there. It's unfortunate that the plot here disappeared. And finally, one of the other ways we're looking at optimizing our machines is via digital twins. So a digital twin is essentially a way of creating a realistic representation of our computer in a simulation. And they have different levels of digital twin, from descriptive to a twin that just looks like your system, your supercomputer, to informative twins that integrates real-time data so that you can learn insights about your system, to predictive twins, so learning, using this twin to predict behaviors of your system, things like when might you find pieces of your hardware are breaking, or can we predict where these things might occur? I'm just going to search for I've now lost my place in these notes because I stopped reading them. Just quickly find. Here we are. So can we use a digital twin for a supercomputer as a monitoring system, just to understand better what's happening on the machine? Can we then use it to predict or diagnose faults on the system? Can we use it to help us design future systems, like understanding whether the cooling system we're using for our current computer would actually support a much larger computer, this type of thing. This is one of the topics we're looking at, and come to near the finish here with this nice image from Oak Ridge National Lab in Tennessee. And what we can see here is the digital twin they've been building of the Oak Ridge supercomputer, which all of these boxes are the cabinets of the system. These are the CDUs here. And this is the full cooling system of the data center that they've modeled in a game engine. And they're allowing you to sort of visualize in augmented reality, and you can see, and it's running a full cooling simulation, so you can see the temperature of different blades, different cabinets. And so this is one of the ways that we're looking at trying to optimize our systems, both for energy efficiency, but also for sort of future operational efficiency. Now, that's all the slides I have. There's a couple of minutes left in the hour, so I would like to just show a couple of videos on the logistical challenges of constructing and delivering our supercomputers, because this is something that people generally don't see, right? I mean, in general, you don't see the supercomputer itself. You see some pretty pictures like I've put on the slide, but you don't get to go to the data center. You don't get to touch things, right? And you don't get to see how these things are built, how they're transported, and how they're installed. I can indeed. So I'll click admit all of them. There we go. And actually, well, while I'm here, I can quickly scroll down there. So there was a bit of a lag in Zoom. Apologies for that. Slides. So the slides have apparently been running behind. Again, apologies for that. But I don't see that we have any current questions in now. So let me see if these. So we've got two videos. One of them is preparing a system for shipment. So, a little bit loud. Let's see if we can turn this down a touch. So we installed our previous generation of supercomputer was called the Cray EX, and we installed one at Gloucester. And this video shows how we packed up the system for shipment. And then I'll show a second video on how the same type of system was installed at a different site. sort of see here that it's not just the cabinets that make up the system. You know, under the floor, there's a lot of cabling, cooling infrastructure, and everything comes in. So it's much more than just the cabinets that make up the full supercomputer. And typically we'll work with a customer way before they get the system to ensure that their data center is designed to host such a system. They typically have to reinforce the floors. They have to have special sort of infrastructure for the power it uses, the water coming in and out. These cabinets weigh about 3 tons each, so as you see, they need some tools to move them around. So that one's on prepping the system for shipment. So it's nice to see sort of what goes on behind the scenes in the factory. And then I have one from the other side, sort of the customer side. And this one's actually, it's another XC, but this one's being installed at Pittstein. Sorry, this one's called Pittstein. It's being installed at CSCS, which is the Swiss National Supercomputing Center. So of course we send engineers along with the system, not only to ensure it gets there, they're very expensive things, but to help get them installed, get it so physically installed, and then get the software all installed, get the system up and running. It's typically a fairly long process from you first getting the system to it being what we call accepted, which means you're essentially happy with it. We've delivered on the contractual terms for the system. Some of our old systems, owned the Cray one, we'd have engineers move to the customer site for 1 to 2 years and help keep the system running. They were a little less reliable in those days. They needed a fair amount of support to keep running. Fortunately, these days they still need support, but perhaps the uptime is better than it used to be. typically have gas-based fire suppression systems in these data centers. If there is a fire, you don't want to spray everything with water while it's running. It usually tends to break things. And so in many of these centers, they have to have special infrastructure to ensure that they can put out a fire without damaging anything. And the one in Sweden I was at recently had special holes in the walls, because if the fire suppression system went off, it filled the room with gas so quickly that the windows would blow out if they didn't have special sort of outlets for the air to escape. I haven't seen one pop up in the video, but we also have these devices that help you lift the blades up. You know, if you're putting a blade in the top chassis, it's sort of up here, and these blades can be really heavy. So we have devices that help you lift them up and slide them in, because they can flex if you're holding it. If you're holding it flat, it can flex and actually crack the electronics. So you can see a lot of cabling. We usually put an artwork on the front there. Here, in the video, we didn't get to it, but on the front of the system, we then usually put an artwork along the whole front, which you'd see in some of the pictures of these machines that go out publicly. So I think that's everything. Thanks a lot for coming along. Thanks for listening. Questions along the way. And yes, if you have any more questions, happy to talk. I think be around for another half hour or something. As I mentioned, there's goodies on the table, so welcome to take any of those. And my email is up on the slide there, so if you do want to talk to me afterwards, feel free to shoot me an email.